Hello and welcome to this new episode of where we discuss mathematics or physics on the board. In this particular video, I'm going to use some method or technique we've seen, which is to actually use a Jacobian of some transformation when we transform coordinates and to change the corresponding volume form. And what we are going to do here is try to use this particular technique to determine how we essentially talk about volumes when we are in curved space, and even better, let's say, in curved space-time. And actually, usually this is a confusing part where people simply learn by heart that there should be this particular factor in there, but without necessarily understanding where it is coming from. So we are going to see that in this video. Right, so here I'm just going to go through kind of basic stuff. I'm not using on purpose, I'm not using the Einstein summation convention just because I have not talked about it before, and sometimes that can be quite confusing, so I'm not going to use it here. I might use it when I'm thinking on the board, but then I'm going to put the sums where they have to be. But the bottom line is that in general, if you want to define the arc length, usually we talk about the arc length squared, and this is often denoted ds squared. And again, very generally, this is going to be written as a double sum over some numbers here that are called like corresponding to the so-called metric tensor or metric tensor components, and then multiplied by the kind of length element that you're going to look at. Essentially, this is a sort of generalization or extension of Pythagoras theorem. And this particular G mu nu here essentially relates to curvature. And so it's going to be independent, let's say, of coordinates if you are in some kind of Euclidean space and everything is going to be equal to 1 and so on. And otherwise it may take many different forms. Okay. Now the thing is that how do we define volume in kind of normal Euclidean space? So if we are in kind of normal, let's say normal Euclidean space, we had actually defined and talked about, let's say in 3D, you would have the so-called volume form, and that's dx, wedge dy, wedge dz, and where essentially it's assumed that that basically dx is perpendicular to dz and is perpendicular to dy. Okay, so they are all perpendicular to each other, so it's a sort of orthonormal basis, and so when you evaluate that stuff, you essentially evaluate the volume of a cuboid. Okay, so that's kind of the bottom line, and that's how you define things usually when you look at measures. Now the problem is that so that's a normal case, and then what you can ask is, okay, in the not normal, so curved kind of space-time, then how do you define that particular volume form? So here you would have dx, dy, dz. So for example, you could say, is it simply dx0, wedge dx1, wedge dx2, wedge dx3? And you can wonder whether that's the case. And it turns out that no, that can't be like this. There are multiple reasons for that. A very simple reason is that often these variables, x0, x1, x2, x3, essentially can be anything you want. So they don't necessarily need to have the dimension of an actual length and so on. So that's why there is a need to come back to something that is much closer to a cuboid, but basically in space-time. Okay, so that's kind of the bottom line. We want to go back to a cuboid use a cuboid as a sort of safe ground onto which to define volume, and then we can basically see how these things transform upon a change of variable. So how do we do this then? Well, the thing is that in general relativity, you have that locally, you can always, that's kind of an equivalent of the principle of inertia. Locally, you can always find a coordinate system that is basically Minkowskian. So essentially, that is flat, and that's a coordinate system where the geometry is going to look flat. Okay, so in general relativity, we can always find a coordinate system for which basically the corresponding g mu nu. So let's denote this coordinate system with primes. Okay, so coordinate system, so x mu prime, for example, for which g mu prime nu prime, so in x prime, is actually equal to eta mu prime, and then it does not I mean it's in this neighborhood, and this particular eta mu nu prime is equal to let's say that, so is equal to 0 if mu prime is different from nu prime, is equal to plus 1 if mu prime equals nu prime equals 0, and is equal to let me check, and is equal to minus 1 if mu prime is equal to nu prime is equal to 1, 2, or 3. Okay, so that's this particular eta mu nu. Okay, so then you can say, oh, but what kind of transformation do I need to apply to actually get that? And so here you want to transform from the x to the x prime coordinates, for example. So let's say you actually go, so let's have a look. So let's say you apply a transformation. So the way you apply transformations on this stuff, you actually say that usually this is how people are going to look at it. You apply a transformation which is the following. So you want to essentially invert this particular thing. Okay. So the way that works is that you're going to find um, um, some transformation. So you've got g mu prime. Well, sorry, need to get this thing kind of right. So we've got g mu nu, so that's where I start from. Okay, and then I want to transform that with some transformation. So I'm going to have t, and then this t is going to have a mu here, and then a mu prime, and then another one here, which is nu, and then nu prime. So I need to have two sums, and I want that to be equal to eta mu prime nu prime. So that's the transformation. So here it's a transformation I'm operating, and that's for mu ranging from 0 to 3 and nu ranging from 0 to 3. So that's kind of what I want to do. Now I actually know what these particular transformations are. They are basically with this t mu prime, they have to be the following. So they have to be dx mu dx mu prime. Okay, and likewise with nu and nu prime. Okay, that's what they have to be here to actually get this right. Because that's a traditional coordinate transformation. If you change, because it's a okay, this by definition is so-called the tensor criterion. So if G mu nu is a tensor, which it is, then it's going to transform in this particular fashion. So with the transformation rule being like this, when we change coordinate system. So that's the kind of thing I'm using here. If you are not comfortable with this, please have a look at the notion of tensor criterion. And that's basically what I'm relying on here, the tensor criterion. So because this is like this, that this is working, then I can try to look now at the determinant of all of that. So one thing you can look at is try to imagine. You can't do that necessarily as a matrix product per se, because these are not exactly matrices. So matrices usually will have a corresponding index upstairs and downstairs. However, you can use the formula, let's say, that let's say I'm going to do that here, that the determinant, I'm just going to do that as if it were something like this. T of G being a sort of matrix here corresponding to this element, and then times T applied twice is going to be equal to the determinant of this matrix eta. That's what I'm going to use. So that's I'm basically exporting without any proof this particular properties of determinant. So the one I'm going to use is that the determinant of the product of two matrices is a product of the determinants. And so here I'm going to have therefore that I've got the determinant of G and then times the determinant of T squared, and then that's equal to the determinant of eta, but the determinant of eta is simply the product of all the minus ones and then plus one, and so that's equal to minus one. So usually at that stage what people do is that they define this thing as being lowercase g. That's how they call that. In fact, yes, they just call that lowercase g. Sometimes they put yes, just lowercase g. And maybe sometimes you can put that double bar around it, but let's call that lowercase g as a determinant of the actual matrix here. And once you're there, therefore, you've got that the determinant of t is equal to 1 divided by minus g and then square root. Okay? Now, that's where we actually look at things. So I'm going to say that the actual volume, space-time volume that is safe to define is going to be in terms of the x prime coordinates. I'm going to say this is x0 prime wedge x d1 prime wedge dx2 prime wedge dx3 prime. And I'm going to say that this, therefore, is equal to, sorry, I need to rewrite that slightly below. So I'm going to say this is dx0 prime wedge dx1 prime wedge dx2 prime wedge dx3 prime, and that's equal to, and that's going to be the determinant. And if you look at how that works, it has to be the inverse of t actually. So it has to be, if I use a formula, so I'm going to put the reference to the formula I'm referring to related to the determinant of the Jacobian matrix. Here this is going to be t minus 1. And then dx0, dx1, dx2, dx3. And as it turns out, d of t minus 1 can be looked at as being essentially 1 over determinant of t. And so what we are going to get in the end is actually the square root of minus g and then dx0, dx1, dx2, dx3. And the reason why this is nice is because then this is in arbitrary, okay, in any arbitrary coordinate system. I'm going to, I can actually write the volume form, and this is the part that comes from the curvature. Now, if you are in Minkowski spacetime, then G, as we've said, is a determinant of the corresponding metric, and so you're going to get -1. So minus 1 is simply square root of 1, and that's 1. Okay, so here, basically, this is something very amenable and very versatile, because once you've started from something that is locally well defined, that is locally kind of flat for this particular coordinate system, then essentially you get this expression for any coordinate system. Okay, this G, by the way, is going to depend on position and so on. So if you were to take some derivative and stuff like that, then you're going to actually get something that is going to matter. Now, I have no space basically to continue working here, but essentially the reason why I wanted to talk about this is because when you look at the so-called Einstein-Hilbert action to try to derive the equations of general relativity, then essentially you've got this particular volume measure element with this particular term that is there, and usually people kind of don't know where it is. Now, on top of this, you would have to add the so-called Ricci scalar, which is going to correspond to the really like the global curvature aspect, not global, but like the local kind of really curvature aspect of the system. And basically that's it. So I hope if you have ever read any book on general relativity, then maybe that can kind of dispel some mystery about where this thing comes from. Otherwise, in any case, I hope it was a good recap. And even if you have never looked at anything like that, then you can see how what we've looked at when it comes to volume forms and also basically the Jacobian formula, how this can be useful down to general relativity. Okay, so basically that's it for this video. If you've got any comments or any questions, please let me know in the comment section. And otherwise, see you in the next video.